All right, y'all. Well, welcome back. We are over, in my opinion, the worst part of the class, which is the first test. Now, I already sent out an announcement. Hopefully you all saw that yes, I believe I gave you all too many questions on it. I believe the difficulty of the questions was fine, but I think it was too many to give you all time to actually think, process, and go back and check your work. So I notified you all that, for one, we'll be curving it in some capacity, and then two, the next test, my thought is to pare it down from 25 multiple choice to 20 multiple choice, and from 2 out of 3 free responses to 1 out of 2. So we will see. I will build, as we get closer, I'll build the test, I'll time myself, we'll see how it goes. Make some adjustments there. Expect the same level of difficulty, though. Expect the problems. That was a good indication of what the problems will look like in the next one. I'll probably do a survey next class just to hear from you all whether or not you thought it looked like the problems that you've seen before, or whether you were caught off guard. I'll do that next time. But one thing I do want to show you all, so I have graded the multiple choice. That was really quick. I was able to do that then and there. That was the benefit of me giving the Scantrons. I could just go home, scan it with my phone. So let me show you all what the distribution of scores look like. So it's a beautiful bell curve. This is just people that haven't taken it or missed it. These are not people that absolutely failed it. That's almost impossible to do. There is a chance. So the average is right around here. It's a 65%, which is better than I kind of expected given how long, the time constraints and things like that. So what I will likely end up doing, I still need to wait on the free response. What I will likely end up doing is curving it by 10 points, get that 65 to a 75. It's a nice little average there. Shift this bell curve over a little bit to the right. But I'm really happy with the distribution. I'm not happy that people did poorly, but that's going to happen no matter what. One of the rules of statistics is take enough data points and you're going to have this distribution. So to me, this shows that at least there's kind of some equivalency in terms of what I'm doing. So this will kind of get shifted over to the right. I will post your all's multiple choice, your free response score on Thursday. So got a couple of people taking it due to makeups, due to excusal policy, that met that criteria. So I will post that score for you all. Now, is that your exam score then? No, I need to wait on the free response scores. I do not know how those went exactly. I know those were tight on time. So once I see those, there is going to be a little bit of creative grading here because I know the time was short. Ultimately, my goal with the test is to evaluate whether you understand the content. My goal is not necessarily to see whether you can do it in a set period of time. And so towards that end, I know some of you may have prioritized the free response. Some of you may have prioritized the multiple choice. So when I get those scores for free response, say you did really good on the free response, but not so good on the multiple choice, I will take that into account, and I'll probably weight that a little heavier for you. Previously, I told you all it'd be like 60% multiple choice, 40% free response. I'm going to kind of adjust that as I see the scores. I'll let you all know what that'll exactly look like. I need to see the scores first before I decide what that is. But I want to let you know if you did prioritize the free response, I do want to recognize that and acknowledge that. If you did well on it, give you the points that you're due. So I'll be more clear on that once I have the information and have it kind of set out, but just know that say you scored really bad on this because you didn't spend as much time on it, but you scored really good on the free response, I will do something to account for that, okay? Ideally, if you did well on both, you're good to go. I also want to remind you all that remember that tests are 50% of the credit in this class. And how does that work out? That means if you've gotten that kind of free 50% from doing all the other work, discussion sections, clicker questions, basically all these kind of freebies. If you get a 50% on tests, that means at the end of 50% on all the midterms and the final, that still gets you a 75% in the class. So that lets you know that when I do post these, if you did score really poorly, that's not the end all be all. If you get 80% averages and you got that 50%, then that gets you an A. Those are my two cutoffs. So when I post these, don't take this to mean that if you got a 50 on the test, your final score in the class will be a 50. Now, the other part, that's why it's 50% of it, to acknowledge the work and effort you all are putting in as well, but at the end of the day, the grade doesn't reflect your understanding. The other thing, and I think I'm pretty set on this, is I'm planning on letting the final exam grade take place of your lowest midterm grade. Okay, I'll send out an announcement about that with the specific details, but basically the final exam is cumulative, and so if you score really well in the final, I will let that replace, say you bombed one of the midterms. The idea being, my grade should represent your understanding, and if at the end of the course you show that you understand it, then I should give you a grade that reflects that. So, the final exam score. So, all of that to say, if this first test did not go well, there is potential for you to kind of rise up again and still get a decent grade. I will say, once I curve these things, basically, if you scored below a 50-ish or below, that's kind of a red flag that something needs to change. So when I post these, and after the curve, I guess they'll be like a 55, 60-ish. If you scored kind of below that, that's a red flag for you. Something needs to shift. I'll go ahead and tell you, I'm not necessarily, I mean, if you have ideas for me, please email me if you have ideas of things I could be doing up here. It doesn't necessarily mean I will do it because there's limitations, but it will likely be something on your end because most of learning happens outside this class. That may look like going to office hours, that may look like going to the help room hours, that may look like going to kind of tutoring, that may mean just spending more time solving the problems. That is some indication of that. And you're welcome to email me if you're trying to figure out what that change needs to look like. So, first test, once I post it, they got it in this week, that'll maybe an indication of, do I need to change some strategies on your all's end? Or, again, you're welcome to email me if there's anything you think I could be doing better. I can definitely improve. Everyone can in life. But just because you send me a recommendation, I will tell you, it doesn't mean I can necessarily do it. There's limitations to what I can do and what I will do. So, there's that. What I want to talk about real quick is you all have a very easy assignment this week. So you have that physics I care about. Basically, the purpose of this assignment is I try to connect the concepts that we cover in this class to things that you are going to be using in the real world. But I do not know all of you individually. There's way too many of you. If you were one of my high school students, the story would be different, but you're not. There's 220, too many. So this assignment, basically, it's very easy points. It's kind of just a off week. There's no quiz this week. Yes, the quiz from last week is kind of closing out today at midnight. But there's no quiz due at the end of this week. This is your assignment. Pick something we've covered, connect it to something that you think is interesting or care about, and write about it and put a picture, because we've talked about the importance of pictures. Pictures show so much information. Ideally, if you can find a picture that kind of labels things or describes it and explains it, that's best. But the purpose of the activity is basically to give you all kind of an easy week as far as there's no quiz, and to give you something that is going to be meaningful. And I will look through these, and I will hopefully learn some interesting connections I didn't know about as well. And then I can incorporate those in future years. So there is a purpose to this. It's not just busy work, but at the end of the day, it also should be a very quick and easy assignment for y'all to do. So there's that. Any questions about this? It says add a multimedia. Basically, that just means a picture, video, just something quick. These will not be graded for a little while because my grader is clearly very busy grading a bunch of free response, but basically if you all get this in, that's a good indicator. If you meet these requirements, it should be all the points, so you shouldn't be too concerned about it. Any questions about this assignment? All right. So we are going to start the next kind of chunk of content. If you all haven't looked at already, we have, so problem set 1 was for test 1. We are now entering the regime of problem set 2, so if you're curious what topics we'll be covering, 1, that's in the syllabus, 2, it's in problem set 2. But the first topic basically breaks down into 2 things. We have circuits, which we're going to get more into. We're going to finish up circuits, get more in depth with those, and then we're going to talk about magnetic fields. That'll cover us for this week and 3 more, so 4 weeks total. So the next test will be, it's on the syllabus. Let me remind you all when that is, just so you can put it on your calendar. So, DC circuits, magnetic fields, Faraday's laws about magnetic fields. So March 30th, and that will be after spring break. So that's nice. You get kind of a little buffer time. I'm looking forward to it too. So March 30th will be exam 2. So kind of, again, keep that somewhere in your head. But we have 4 weeks worth of content plus a spring break thrown in before then. Okay, so circuits. This is both going to be stuff that you've learned and obviously some new stuff. So the stuff that you've already learned that we need to remember is we need to remember capacitors, which we saw in the last test. They're the 2 parallel plates that store charge. Capacitance equals Q over V. We're going to use that today. We need to remember resistors, what they are. They are things in a circuit that resist current. V equals IR. And we need to remember what current is. Current is the We say it's positive charge moving when the reality is it's actually electrons moving the other way. These are the things moving in the wire, and the voltage is what's making it happen. Remember we said voltage was like height, current is like the things going down that hill, and then resistance is the things slowing them down. So we're going to need all those concepts when we talk about the circuits today, because basically we're going to build more complex circuits. Last time we just had a battery resistor, and that was as hard as it got, or a battery capacitor. Now we're going to put multiple resistors, because that's what the real world looks like. The real world isn't just a battery and a resistor. Every single thing in this room is multiple connected to a power source. Case in point, you hit the light switch and multiple things turn off. So this is all stuff that we saw before, but we're going to be using today. What are we going to be covering today? We will be talking about the junction rule, which will have to do with how current kind of splits up. We're going to talk about how voltage actually changes in a circuit. So we start kind of at the positive end of the battery, and at the end we get to the negative. How does the voltage change? When does it change? And we're going to talk about the equations for adding resistors in series and parallel. We'll get to capacitors next class. We'll also define what the heck series and parallel are. That'll be important. And actually this last one is not going to come up, so let me just actually knock that out. We are not going to be doing RC circuits. So previously I've done that in classes, but that wasn't covered. So resistors and capacitors in series and parallel, and how current and voltage changes in a circuit. All right, so first off, I'm going to introduce what the heck a battery is. This is not going to be tested. I'm mentioning it because we're going to keep saying batteries, and it's useful to know. You could basically think of batteries like a ski lift. Remember, we keep saying voltage is like height? Well, you got to get those things to the top of the hill in the first place. How do you do it? A battery. Battery is kind of like our ski lift. It has chemical reactions that take the electrons from the negative terminal. Well, they take them from the positive terminal, they move it to the negative terminal. Where do they get the energy to lift them up? From the chemical reactions happening. Those chemicals kind of run out, just like any chemical reaction, baking soda and vinegar. You all have done that as a kid, volcano, maybe as an adult. Eventually those things stop reacting because you run out of baking soda and vinegar. They've all reacted together. Batteries are the same way. Rechargeable batteries, you can kind of just reverse that reaction by putting some electricity through it. So there they are, batteries. That's how they work. You do not need to know the specific details of it in this class, but I wanted to mention it because we are going to be mentioning batteries so much. So here's where we get to the things we need to know about. Current, this is kind of an important concept. Current is constant along the branch of a circuit until it hits a junction. Whereas voltage is constant before and after junction. So we have this very complex looking picture here, and I just put, it's got batteries. Those are, let me label what those are. The batteries are the ones with B's next to them, makes sense, hopefully. Battery right here, and then our resistors are clearly the ones with R on them. These are junctions. We're going to see these on kind of the next slides. A junction, you can almost think of it like where a road splits into multiple roads. It's a place where the wire splits. There's more than one path it can take. It goes in, and it's got choices. So a junction is where multiple wires meet together. This corner is not a junction. That corner is not a junction. Why? Because the wire doesn't split. Yes, it bends, but so what? Every wire, you can bend it. It doesn't make it a junction. A junction, it needs more than one path. And you can think of road, like I'm going to use the analogy for roads a lot. Think of it like a road that hits a traffic light. Cars have a choice. So say the cars are coming in this way. They have a choice of either going that way or that way. And so, the number of cars going in will equal the number of cars going out. Say I have 10 going in, maybe 5 go one way, 5 go the other. That's that first thing. Current is constant along the branch. So if I call this I1, current is constant everywhere here. But the second I hit a junction, the second I hit a point where it can split, it splits, it changes. The second I hit, just like a road with cars, it doesn't matter if that road gets wider or narrower, it has the same number of cars on it. You can think of that like the resistors here. The amount of cars on a road, doesn't matter if you go from a highway to a 2-lane road, you still have the same amount of cars. They can't just, unless one exploded or pulled off to the side, but your electrons are not exploding or pulling off to the side. You're not having a buildup of charge, hopefully. But once they get to an intersection, They split. The current can split and take different directions. Those electrons have choice. Choice, personifying again these things. So voltage is constant along a branch until it hits a junction, but it's very important. So current is constant before it hits a junction. Voltage will only change when you hit a battery or a resistor. Voltage will only change when you hit a battery or resistor. So let me kind of color code this. So let me take this whole kind of picture and slide it off to the side. The purpose of this first one was to show you that current is like when current changes and when current stays the same. Let me make a copy to show you all when voltage stays the same and when voltage is changing. Because this is a very important concept. This is a very important concept to understand. When does current change and when does voltage change? If you understand this, everything else will be easier. If you don't understand it, you will still likely be able to do the math and all those kind of things, but your understanding of electricity will just be a little weaker. So, voltage is the same as long as, and this is going to come up in another slide as well. So the voltage on that red line is the same. It's before I've hit a resistor. It's all on a wire. It doesn't matter if that wire splits. Again, think of a road. The height of a road doesn't need to switch just because there's an intersection there. They can still be flat. But then maybe later on. So the voltage there is all the same. The voltage here is all the same. I'm basically just drawing lines, different colored lines between resistors and batteries. Just using different colors to draw. As long as I haven't hit a resistor or a battery, my voltage is staying the same. There you go. Whole bunch of different colors just between all the, what do I have left? Yellow. So each of these is its own voltage. And we're going to learn how to kind of calculate that. We're not going to do a circuit this complicated. So that's a V. We'll call that one V1. Call this one V2. Each of these different colors is going to be a different voltage, because it's going to change when it hits the batteries, and we're going to learn how to calculate that today. Don't worry about what the exact numbers are in this picture. It is doable to find it on this picture, but it would take a good amount of time, and we're not going to worry about it. But I just want to show you all everywhere. It doesn't matter that the wire splits, voltage stays the same. Current does change when you hit a wire. Okay? Current does change when you hit a junction. All right, so we're going to be exploring that a lot, but I just want to emphasize this is really important. Understanding when voltage changes and understanding when current changes, because everything after this is going to use that. Every equation I introduce is going to need those concepts. Everything about resistors and capacitors, if you understand that, the rest of the content will make sense. If you don't understand this, that's okay. You'll still be able to do the problems, stuff like that. But one of the rules in physics, if you understand the concepts, the math is easier. Okay. Cool. All right, so first off, junction rule. Talking about current and how current changes. Very straightforward. Current in equals current out. If you add up all the current going into a junction, it will equal all the current going out of a junction. Again, think of the car analogy. If 10 cars go in, 10 cars have to come out. I don't care which way they came out. However many, there's 2 doors into this room, and there's maybe 100 students in here. Doesn't matter which doors you all came in. At the end of this class, hopefully 100 students are leaving this room. Otherwise, that means someone's sleeping in here. I don't know. It would be bad. What goes in must come out. If we look at this picture, what goes in? Just the arrows that point towards the junction. So let's maybe label all the green ones here in. So I1 is pointed in. I2 is pointed in. I5 is pointed in. I4 is pointed in. They're all pointed inwards. I3 and I6 are pointed out. They're pointed away from it. So you can see my equation right down here. Add up all the ones that point in equals all the ones going out. Very simple equation. Why? It's the same reason that I just told you all. The amount of people coming into this room better equal the people coming out. Otherwise we lost people, or people combined, or people split into more people. Basically things that don't happen. Same thing here. Whatever goes in must come out. Current is literal electrons. Whatever goes in, I better get those electrons out. Otherwise they're building up at that point, and that's not what we want to be. That's not happening in a circuit. None of the circuits we're talking about, that's happening. What goes in must come out. We'll do a few practice problems on that. All right, so speaking of problems, let me actually start up the clicker process. But here's the first problem I have. It says, based on the image below, what is the value of I4? I am not going to give you all any hints here. I just want to see how it goes. As needs be, I'll give some hints. But here's my junction. I have an I1 equals 2 amps, and that arrow is pointed towards that junction. I have an I2 equals 5 amps. That's also pointed towards that junction. I have an I3 that is 7 amps, also pointed towards that junction. And I have an I4 equals mystery pointed away from it. What's I4 equal? Remember the mantra, what goes in must come out. That's when we think about current. And it's very important that we're thinking about current here and not voltage. If this is voltage, it'll all be the same. If this is voltage, every single one of these would be the same number. But it's current. All right, we'll go to like 115. Math here is pretty simple. It's just a matter of, don't worry, there'll be another one after this to practice. 5, 4, 3, 2, 1. All right, so let's go ahead and solve it out. The equation was these. This is the symbol for sum, capital sigma, capital Greek letter sigma. Add up all the currents going in equals all the currents going out. Which ones are going in? I1, I2, I3 are all going in. I4 is going out. So this math problem is pretty straightforward. I1 plus I2 plus I3 equals I4. So 2 plus 5 plus 7 equals 14 amps. Boom. And from what I saw, a lot of us had that down. Awesome. If not, this is the idea. We'll get another practice one in. So 3 pointed in, 1 went out. So they all added up nicely. Now, let's go ahead and do it. If 2 point in and 2 point out. I have I1 equals 6 amps. I have I2 equals 5 amps. I3 equals 7 amps. And I4 equals mystery. Figure out which ones point in, which ones point out. What goes in must go out. And the good news is, if this is easy, I can almost guarantee a problem like this will show up in the next quiz or test. This will be a very easy test question for me to ask. All right, we'll go to 115 again. 5, 4, 3, 2, 1. All right, so same old, same old. I'm not going to write the equation again, but I will label which ones go in and out. So I1 goes in, I2 goes in. They are pointed towards that dot in the middle, whereas I3 and I4 are pointed away. So we have I1 plus I2 equals I3 plus I4. We put in our numbers, so 6 plus 5 equals 7 plus I4. Simplifies to 11 equals 7 plus I4. We subtract that 7 over, and we get 4 amps. There we go. 4 amps. If you missed this, just please look over this later, double check the math. Maybe it was just a math error, maybe it was a which ones go in, which ones go out error. Hard for me to say. All right, so I've already mentioned this. So we just talked about current. Great. Current changes at a junction. And I've already said this. Voltage is constant until you hit a battery, a resistor, or a capacitor. Basically, who cares where that wire is moving? until it hits something that looks different than a wire, the voltage stays the same. So until it hits a battery, batteries look like this. Until it hits a resistor, resistors look like this. Until it hits a capacitor, capacitors look like this. Until it hits one of those things, it does not matter if it splits into 5 different paths, 10 different paths. Who cares what happens? As long as I'm on the same wire and I haven't hit something, the voltage is constant. Once you hit one of these things, the voltage is going to change. Battery, real straightforward. Remember, it's like a ski lift. How high does a ski lift take you? As high as the hill is. So whatever that ski lift is, say it's a 6-volt battery, that's how much it's going to take you up. Or a 9-volt battery, great. That's the voltage change. My voltage from the negative to the positive goes up 9. That's my height increase. For resistors, V equals IR. We're going to use this equation a lot in this section. V equals IR. So say the current through this resistor is 2 amps. Say that this resistor is 3 ohms. Then V equals IR. So my voltage drop will be 2 times 3 equals 6 volts. And in the capacitor, if I gave you how much charge is on it, and I gave you the capacitance, you would solve for it with that. So say Q equals, let's make up some ridiculous numbers just to make the math easier. 3 coulombs, and say it's a 1 farad capacitor, then V would be 3 over 1, which is 3 volts. So fairly straightforward. V equals IR is the most important out of all of these. We're going to use that the most. Yes?
So when it passes the battery, it becomes the voltage of the battery?
It ups it. It ups it. Say the voltage was like 3 before that battery. Then it goes to the battery. It goes up 9. So now it becomes 12.
Okay.
Yep. So say it was, remember, whenever we talk about voltages, we talk about height. It's an implicit difference. So say we were at 3 on this left side. Then we hit this battery, we're going up 9. So 3 plus 9 will get us up to that 12. If we're going the other way, it lowers it. If you go from the positive to the negative terminal, it goes the other way. If you're going up the ski lift or down the ski lift. Positive end is higher, negative end is lower. Resistors, they drop in the direction of current. And we're going to see that in some slides in the future. That's why I'm not drawing too much right now about it. All right, so let's explore the whole resistors one in particular. So here we have a circuit where I have a battery and 3 resistors, and we're going to learn that this is series. We're going to learn this series, but for now, there's one path. Current just goes in a loop forever and ever and ever and ever. Again, think of it like skiing. You go up the ski lift, you go up in height, and then we hit our resistors, and those are each various drops, and we end at the bottom, and we go back up the ski lift, and it's a never-ending thing as long as the battery's got chemicals in it. So when we go across the resistor, we go in the direction of current. So in this case, the current's going to flow from the positive end to the negative end. Voltage is dropping. Because the positive end of the battery is high, the negative end of the battery is low. If this is a 12-volt battery, we could think of this side as 12, we could think of this side as 0. So, by definition, when we get to the 0 side, we're at the bottom. When we're at the 12 side, we're at the top. I've got a graph on the next slide that kind of shows that and shows as we go through each resistor what's happening. So voltage drops when we go across it and in the direction of current. If you went backwards, you're going uphill. So if I went backwards instead of clockwise, I went counterclockwise, so I'm going down here, then I'd be going up, and I'm at the top of the hill, and down the hill, and so on and so forth. So let's look at a graph that kind of shows exactly that. There's your battery, your ski lift. When you go across the battery, the voltage goes up. You're going through your circuit, through the wire, until you hit a resistor. The resistor drops the voltage some. You're going along the wire, so voltage is the same. You hit a resistor, so my voltage drops. You're going along the wire, so voltage is the same. You go down the resistor, the voltage drops. So, just to kind of iterate, let's draw some colors on here. Voltage is the same here. Remember, as long as you're not hitting, and maybe these lines don't match up super nice, that's why I'm coloring over them. As long as you're not hitting something, voltage stays the same. The second you hit that resistor, it drops. How much does it drop? V equals IR. V equals IR. I is current. You may think, wow, that sounds going in a circle forever and ever, but it needs to keep adding juice to it. It needs to keep going in a circle for it to keep running. Whatever device you may have, you're better hoping that currents keep going, because the second it stops, your device stops working, whatever that may be. All right, so let's kind of practice this. Let's practice that V equals IR. So there's another picture of the same thing. There we go. If we loop the other way, So when we went clockwise, we were going up and then down, down, down. As we go counterclockwise, we're going up and then down. You're just changing the direction you're traveling. So when you're going in the direction of current, here's the direction of current, you're going downhill. If you're going opposite to the direction of current, you're going uphill when you go across a resistor. All right, so these are just some of the rules that basically summarize all that. I'm not going to spend too long on here. It basically says exactly what I should. When you go in the direction of current, voltage drops. When you go opposite direction of current, voltage increases. When you go from negative terminal to positive, voltage increases. When you go from positive to negative, voltage decreases. This is just all the rules that we kind of said in one nice little summary slide. All right, let's practice some of this. So, in the circuit below, and something I do want to point out, there's no junctions in this circuit, which means current is constant. Current doesn't change. Maybe the highway gets thinner at some points and wider at some points, but the current is the same everywhere. The current is the same everywhere because there's no junctions. So, in the circuit below, if I equals 2 amps, which means I equals 2 amps here, I equals 2 amps here, I equals 2 amps everywhere, because there is no junctions. There is nowhere for it to split. The voltage is changing because there's a whole bunch of things in it, but the current is the same. So if the current is 2 amps, in this case it's 2 amps everywhere, what is the voltage drop across R1? I specified drop, so I just left them all as positive. We're insinuating that that is a decrease. So I'm not going to put a negative sign in front of it because I already said drop. So, and I'm never going to ask you, is it negative or positive per se. I'll just say, where's the voltage drop? And you'll give me a positive. All your answers will end up being positive. But it is a decrease. So, 1 ohm resistor is R1. Current is 2 amps. 12 volt battery. R2 is 2 ohms. R3 is 3 ohms. What's the voltage drop across R1? And the trick to this is remembering what was the equation for the voltage drop across a resistor. What is the equation for the voltage drop across a resistor? And it's the equation we're going to use again and again and again and again. The beautiful thing is it's nice, easy numbers. As with most of these kind of, I would consider still, I don't know if I consider a concept question, but it's math you can certainly do in your head. All right, we'll go till 1:30. 2, and 5, 4, 3, 2, 1. All right. So, what was our equation? V equals IR. V equals IR. So what's the voltage drop across 1? 2 times 1, which is 2. There you go. The voltage drops 2 volts across R1. Spot on. Now, the next problem will be building on this. There's a punchline at the end of these 3 problems in a row. In the circuit below, current still 2 amps, same exact circuit. What is the total voltage drop across R1 and R2? What is the total voltage drop across R1 and R2? So you just did it for R1. That gave you a drop. Gave you a hint. If you get the drop for R2 and you just add those numbers together, you get the total drop. If one drops you a certain amount, the other drops you a certain amount, add those 2 together, bam. That gives you the total amount of drops. So what is the voltage drop across R1 and R2 together? And so to kind of visualize this is basically asking, hey, what's the difference in voltage from before R1 to after R2? That's a rewording of this problem. What is how much does the voltage drop before, if I go from the beginning of R1 and the end of R2? All right, we'll go to 110. Five, 4, 3, 2, 1. All right. So I told you all that the total voltage drop across R1 and R2, we just kind of add those. The voltage drop will be adding those two things. We already got V1, so let's go ahead and get V2 really quickly. It's just the current. It's the same current. Remember, current is the same until you hit a junction, and there's no junctions in here. Times R2. So we're going to get 2 amps times 2 equals 4. We already said V1 equals 2 from the last problem. 2 plus 4 is 6 volts. All right. And we're finally getting near to the end of the punchline, so great job. I think most of y'all got that. Spot on. The last one, maybe you can guess the pattern. What is the voltage drop across R1, R2, and R3? So just to visualize that, so here's the beginning. What's the difference in voltage between those 2 points? Same exact circuit. Current is 2 amps. I have a R1, which is 1 ohm, R2, 2 ohms, R3 is 3 ohms, 12-volt battery.
Did you start the clicker?
I did not. That's really hard to answer if you can't answer. Thank you. I appreciate that. All right, we'll probably go to like 40 seconds. In 5, 4, 3, 2, 1. All right, so we ready, so, same idea, V1 plus V2 plus V3. We've already done V1 and V2, so let's just do V3 real quick. I times R3, it's the same I because there's no junctions involved. Really important that I keep reiterating that. Current is the same because there's no junctions, so you get 2 plus 4 plus 6 equals 12. And maybe you all realize something. 12 is the voltage of the battery. Look at that. We went down the entire hill. And if you look at this, you can kind of see this, so let me go ahead and mark that as correct. You can see this 2 different ways. Remember, I told you this voltage difference is the difference from this point to this point. Well, I asked you all to find it kind of through this way, but let's do it the other side. There's just a bunch of wires in a battery. How much does the voltage change? When we look at this side, it goes from 12 to 0. So there you go. That's the idea. Just really trying to hammer what is voltage, what is current, all these things, and seeing that each battery drops at a certain amount. At the end, you get to the bottom, ski lift takes you back up, down you go again. On and on and on and on. All right. So, I've already mentioned these words, but now I get to define what they are. There's 2 ways to set up resistors, and basically, these are the only 2 ways, but you can do combinations of them. Series and parallel. Series, they're in a line with each other. There's only one path to take. There's no junctions between them. There's only one path from one end to the other. They're in series, kind of like the World Series of Baseball. Each game happens one after the other. In parallel, they share the same junction, or maybe a better way to put it, they share the same voltage on each side. That's what I'm actually going to be kind of encouraging more so when you think about these. So, in series, no junctions. So the current is constant. In parallel, and I'll draw this in a second, the voltage is going to be constant because they each share the same wire. on each side. They each share the same wire. Remember, voltage does not change until you hit a resistor or a battery. Voltage does not change until you hit a resistor or a battery. So, we've kind of really hammered home that current is constant. Let's go ahead and just quickly draw on here why voltage is constant. Remember, voltage does not change. Doesn't matter that there's junctions. Voltage only changes when you hit a resistor, capacitor, battery. That side is just a bunch of wires. So, the voltage on this side is the same. We'll call that like V1. That means on the other side, I've hit a resistor, so the voltage is going to change, but they're all sharing it. That's V2. And if you measure the voltage drop across any one of these, V1 minus V2, V1 minus V2, V1 minus V2, V1 minus V2, you kind of see it there. Voltage is going to be the same because voltage on one side is the same, voltage on the other side is the same. V1 minus V2 is the same for every single one of them. Very important, I bolded, current is constant, voltage is constant for series and parallel. If you can remember those things, that's going to help you a ton. If not, you'll have a little bit of a challenge with these problems. Okay, now I'm going to jump over to a simulation. I've used this one before. Remember that website FET that I talked about? FET's got a bunch of awesome simulations, and I've used the circuit one before. I'm going to use it again because it helps us kind of see it. So I've set up both circuits. I've set up a parallel circuit and I've set up a series circuit. So here's my series circuit. I haven't connected. Here's resistors, 2 resistors. There's only one path, no junctions. It doesn't matter. I'll play around with these resistances. You can see switch is open, so nothing happens. I close it, and bam, look at them go. Now, remember that current flows. So there's current, which goes from the positive end to the negative end, when the reality is electrons are actually going the other way. We'll use current from now on. Just remember that electrons, that thing's actually flowing. And notice that the speed of these arrows is the same everywhere. Even if, let me make it move a little bit quicker. I can up my voltage. I can make my tail a little taller. I can make this resistance way different than the other one. And current is still the same everywhere. It does not matter that I go from maybe a 4-lane highway to a 2-lane highway. The same amount of cars got to get through. Either way. So the current is the same everywhere. There's this nice little ammeter over here that measures current, and I can drag it, and you can see that the flow, current just describes how basically fast they're moving, how many are moving through it. It's the same everywhere. But the voltage is different. The voltage drop, remember I have to measure 2 points to measure voltage because I have to take that subtraction. There's the voltage drop across that one, 55.35. Here's the voltage drop. If you all have never used a multimeter, it's a great skill to have. It basically works exactly like this. You can test your battery's voltage. 5.65. That one's smaller because smaller resistance. If I add those two numbers together, ta-da, I get the voltage of the battery just like you all did before. A multimeter, you have the 2 points. Fun fact, buy a multimeter, they're super cheap, lets you test your battery to make certain it's dead. Your battery in your car should be 12 volts. You just literally put the things on each lead. If it says less than 12, that's bad. You can also test your alternator, and if your alternator is working, your alternator is the thing that charges your battery in your car. If your battery is 12 volts, your alternator's got to push more than 12 volts to charge your battery. Your alternator should be giving you about 13, 14 volts, so when your car's running, you can just put the leads on there. If you're reading 13 or 14, good, your alternator's good. If you're reading less than that, your alternator is not working right. So, there you go. There's your fun, useful, real-world fact. So there you go. There is my series circuit where voltage is different on each of these, but the current is the same. When we jump over to a parallel circuit, we get all sorts of interesting things. Oh, and I do want to point out one thing here. Notice that once the current, remember current's the same everywhere, so if the current stops at any point in the circuit, it stops everywhere. Series circuit, once I turn it off, everything stops. Just like, remember we got to get from one end of the battery to the other, so there's only one way from your house back to your house, and that road's broken, well, unless you can go backwards, and these can't really go backwards. So, there needs to be a path from here to here. If it's broken, no go. Here is a parallel circuit. Let me go ahead and just turn them all on. So there you go, look at them go. Notice, we see that current splitting. Those electrons, well, let's do current again. Let's do the appropriate one. These arrows have to choose a path. They will choose the path of least resistance. But let me show the voltage first. Voltage is the same. Voltage, if I put this prong here, and I put it needs a difference, it is the same everywhere. The voltage difference across these is the same because the voltage on this entire right side is one value. Everywhere here is one value. The voltage here everywhere is one value. So if you subtract those two numbers, you get the same no matter where they are. 9 volts, I can move this red one down here. I can move this black one. It does not matter as long as one is on one side and one is on the other. The current is changing, and I can get a little... Let me change these resistance values because otherwise they are going to be the same. So let's set this one to, it doesn't matter. I'm just going to pick a random number, in this case 36. Notice that one is faster, one is slower. Things take the path of least resistance. Just like if you were driving your car, you would probably pick the highway over that back road that's got only a couple lanes and this has got 4 lanes. I can measure my current and see that the current here is 1.39. They're not moving that fast. Here is 5. It's moving faster. Current is changing, voltage is the same, whereas in the series circuit, current was the same, voltage is changing. They flip. Okay? All right. One thing I want to point out that's special with parallel circuits is, again, think of that road analogy. If one of the road breaks, the other one still works. So parallel circuits are useful when you want something where I can turn one off and the other stays on. There's multiple light switches in this room. I can turn off the lights to various parts in this room, and I could turn those on. So these front cam lights that I all just turned on, they're in series with each other. I hit one button, and they all turned on. But they are in parallel with those ones back there. So I can turn the front ones on, I can turn those off, the back ones stay on, I can turn the back ones off, the front ones stay off. Parallel lets you turn off one and the rest stay on. It'd be a dream if our Christmas lights were all in parallel, but that would be a wicked amount of wires that we can't fit in it, so usually various stretches of them are in parallel with each other. If I turn this one off, then it all stops. If I turn this one on, it works. And here I kind of have one. If I turn this off, they all turn off because there's no path from this positive into the battery to the negative. There's no path. So as long as there's a path, current will flow. And we can do a short circuit real quick. That's kind of a useful thing to know about. A short circuit, I keep saying current takes a path of least resistance. Well, what has the least resistance of all? A wire. A wire has almost zero resistance. And so if you have a circuit where maybe you have 2 light bulbs hooked up to it, and somehow that wire, there's somehow maybe these 2 wires here and here are really close together and the insulation frays and they touch, it's called a short circuit, and this can be dangerous at your house. This is why Christmas lights can be dangerous. If those wires fray, it will skip the lights completely. It will take that wire path. There's fire there because current. Whenever we talked about power before, most of the ways that power shows up in a circuit, P equals IV, is heat. That energy gets consumed as heat. It's literally a bunch of electrons moving through a wire very quickly, smashing into atoms, and that's going to give them energy in the form of heat. That wire will get very hot. And Christmas trees have a tendency of getting dry over time, and that's why they can cause house fires. And that's why you want circuit breakers. If you have a fuse is made to break at a certain current. It's made to melt and break and stop the thing. So your air conditioning unit, almost any major appliance in your house has a thing called a fuse in it, so that if the current reaches a certain value, it breaks instead of the rest of your equipment breaking. And if it breaks, that's basically, imagine this is my fuse, this wire literally just like disintegrates. It literally breaks apart, and then it stops that from happening. So, there you go. All these fun facts that you don't necessarily need to know, but are useful. All right, so we've introduced series and parallel circuits. Now we need to we're getting to some equations. It's been a lot of concepts. That's pretty much how our Tuesdays go. We'll get into the math pretty soon. Resistors in series are really pleasant. If we want to add up all these resistors, say, man, that's 4 resistors. I don't want 4 resistors. I would really like to make my life simpler and just make this into 1 resistor. I can do that. I can basically pretend like these 4 resistors in series are 1 resistor. How do I get it? Add them up. Add up R1 plus R2 plus R3 plus R4, and you get the R net. I will quickly derive that. You don't need to know the derivation, but I will do it just so you can see where that equation comes from. It's not just out of thin air. The idea is, remember, the voltages added up. We've done that. We said we found the voltage drop across all of them was V1 plus V2 plus V3 plus V4. We saw that. You all did that. Let's put some numbers in. V net is I times R net equals I times R1 plus I times R2 plus I times R3 plus I times I4, R4. And we remember that critical rule. Notice I didn't label those I's because they all get the same current. In series current is constant. All these I's are the same. If I had really wanted to, I could have called this I net and called this I1, I2, I3, I4. But all of those are the same. In series, current is constant. So, bam, bam, all the I's go away. They all divide out, cancel out, and you're left with the original equation. R net, I'm going to move this down a little bit just so it's not too smudged in there. R net equals R1 plus R2 plus R3 plus R4. All the I's go away. Bam, there you go. There's the equation. There's the derivation. So that's how you add them up in series. Really easy, really nice. Why do you do this? Because it's a lot easier to work with one resistor than it is with four. And we're going to see some problems where you kind of have to do it to solve some variables. All right, so speaking of which, what's the net resistance in this circuit? Boom, go. It's the same circuit that we looked at before. Series circuit, there's no junctions going on, just one path. I have a 12-volt battery. R1 is 1 ohm, R2 is 2 ohms, R3 is 3 ohms. And this slide will be very nice because not only will it let you practice the R net, it will show you why we get R net. All right, thank goodness all of us are doing awesome at this. Very straightforward, you add them up. We'll go to 1 minute. So R net equals R1 plus R2 plus R3 plus however many are in series with each other. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so it is as easy as it seems. R net equals, I have 3 resistors, so R1 plus R2 plus R3. It does not matter which is which. In this case, they're labeled, but it does not matter because addition works that way. So equals 1 plus 2 plus 3 equals 6 ohms. Easy numbers. Makes an easy problem. Now, here's where I can show you all something. So what you are doing, I'm going to go ahead and minimize this. Just as, that unfortunately shrinks those down. Whatever. I will plop it off to the side. What you all are effectively doing, I'll actually make a new slide, give myself as much room as possible, is remember you are taking this circuit and you are changing it from 3 resistors to 1 resistor. You are taking this circuit and you are changing it from this to this. 1 battery, 1 resistor, which we call R net, which we just said is 6 ohms, and we said this is 12 volts. All right, I want you all to think for a few seconds. What is the voltage drop across this 6 ohm resistor? What is the voltage drop across it? And a reminder to you, what does that mean? If I took the voltage here and I subtracted the voltage on the other side, what value would it be? Just think in your head for a second, see if you can get that number. Give you a hint, it's as obvious as you would hope. It's 12. The voltage drop across R net is 12. It's the voltage of the battery. Remember, there's 2 ways you can think about this. The voltage drop across here is the same as the voltage drop across the other side. So it's 12 volts. Here's why this is useful. V net equals I times R net. We can solve for current. You know V net. V net is 12. We don't know I. We do know R net. Do some quick algebra. 12 over 6. And you see where I got that 2 amps that I've been giving you for every other problem. Previously, we could not get the current with that situation. Ta-da, you got the current in every single resistor. Not only is the current through the net resistor 2 amps, the current through this one is 2 amps, the current through this one is 2 amps, because it is a series circuit. The current through this one is 2 amps, the current everywhere. The current through the battery is 2 amps. There is current flowing through that battery, it's 2 amps. The same everywhere. So, this is how you solve for current, given resistance, resistors, and voltage. Very useful thing. All right, so we just did series. Let's move on to parallel. I'll leave this for a few more seconds. I think. Condensing down circuits basically lets us get the current and then work backwards. We're going to be using that a lot in some of the more complex problems in the problem set, where you have a combination of series and parallel together. And you'll work your way backward using the rules that current is constant in series and voltage is constant in parallel. So we'll do one of those together. Maybe not today, but tomorrow. All right, so let's jump over to parallel. Parallel, the equation is a little bit grosser. 1 over R net equals 1 over R1 plus 1 over R2 plus 1 over, however many you have, so on and so forth. And I'm going to make your all's life maybe a little easier. So if you want to solve for R net, I'll let you show this algebra, like investigate this algebra for yourself. So 1 over R net equals all that nonsense. So if I want to solve for R net, what I end up doing is taking all that nonsense and doing 1 divided by that. Okay? So if you actually want to solve for R net, and you can check the algebra for yourself on this, however many you have. You do 1 over all that nonsense, and that will give you R net. I'm going to maybe make this a bit more clear, just so we... These equations are equivalent. All I did was solve for R net. Previously it was in the bottom. How did I get it not on the bottom? You multiply to the side, divide all that other nonsense to the left side. So R net is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. You will need to be careful when plugging this in. Now, something I want to point out here that I maybe didn't emphasize as much as I should have on the last one. In series, the net resistance is always bigger than any resistor, because it's literally addition. It doesn't matter what you add to it, it's going to be a bigger number. 1 plus 2, 3. 3 is bigger than 1 and 2. It doesn't matter if you're adding a bunch of positive numbers, you always get a bigger number. In this case, it's the opposite. R net will always be smaller. So if I take this circuit, remember what we are doing is we are converting this circuit, which had 4 resistors in parallel, to just being 1 resistor. We are mathematically taking those and saying, hey, if these were 1 resistor, what would that resistor be? And it will always be smaller than the smallest R. It will always be smaller than the smallest R. Why? I've got 4 different roads here to travel. Imagine this is a 2-lane road, a 6-lane road, a 2-lane road. Basically, just add all those lanes together and you got yourself like a superhighway. Of course, the net resistance is going to be smallest because there's so many each one of these is a different path I can take. If I combine them all into one, then I've got a whole bunch of paths in one place, kind of thing. Again, think of them like each lane of a highway. Just take all those lanes and put them next to each other and you got a superhighway. That's basically what you're doing here. So, let's practice the math. R net will always be smallest than the smallest R. So we have a circuit here. It may look a little different, but it is a parallel circuit because all of these share the same voltage on one side and the same voltage on the other side. That's the key to figuring out parallel. They all share the same wire on one side. Even if that wire splits, it doesn't matter. They all share the same wire on one side and they share the same wire on the other side. These are kilo ohm, but my final answer is in kilo ohm, so you don't really have to do the conversion. I have a 9-volt battery. R1 is 10 kilo ohms, R2 is 2 kilo ohms, R3 is 1 kilo ohm. What is the net resistance in this circuit? This one you definitely need a calculator for. Unless you realize something a little nice here about the answers I've given you. There is only one answer that makes sense. All right, we'll go to 205. Maybe a little longer. I see people still thinking about it. We'll keep going. I see people still working it out. All right, we'll call it at 2:30. Five, 4, 3, 2, 1. All right, so let's pull our equation. I'm going to go ahead and take the one that's a little simpler. R net is 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over 10 plus 1 over 2 plus 1 over 1. Now, before I even plug this in the calculator, I can show you all how you can get the answer, because it's a multiple choice question, without doing any of this math. Remember the key phrase that I mentioned in the last one. The net resistance is always smaller than the smallest resistance in that circuit. So, what's the smallest resistance in that circuit? 1. There's only one number up there less than 1. It's this one. That's the only option. It's the only one whose that's smaller than that. But let's prove it to ourselves. We'll just plug that into our calculator. 1 over 10. I'm going to say I'm plugging it in. I've done this problem several times now. You should be getting 0.625, but just to be careful, do it. You can plug this whole thing into your equation. You just need to be careful to use appropriate parentheses on your calculator. If you really want, do the 1 over 10 plus 1 over 2 plus 1 over 1 first, and then do 1 over that. But you can honestly plug this whole thing in one go. That's what I prefer to do, because the less times I plug things in my calculator, the better. You just got to be careful with your parentheses. And yep, you get 0.625 ohms. Here's my little ohms off to the side. A little cramped. But the nifty thing with this problem is you can kind of figure that out without even actually solving it, just to prove a point. All right. I didn't quite show you all how that was derived, so I'm going to go back and quickly show you all. If you want to know, probably don't. I know what it's like derivations. But real quick, for those that are curious, I'm going to show you all where this derivation comes from. It's very quick and simple, just like the last one. All you have to remember, so where does this equation come from? All you have to remember is what is constant in parallel. In series, current was constant. In parallel, voltage is constant. So, we got this, plop this over here. So previously for series circuits, we added up all the voltages and said they were the same. Well, here they all have the same voltage, so what adds up? The current. We got a bunch of junctions here, y'all. We have a current going in, and it basically splits into 4 different paths. We got a path here. You could kind of think of it like a path here. 4 different paths that current splits into. One there, one there. In each of these, we'll call this one I3. This current splits, junction rule, I4. Well, I made my life a little. We'll call this I net. Color code everything, so when y'all look at this later, it makes sense. I1 and I2. There we go, beautiful. So, junction rule, current in equals current out. That current comes in, it splits into 4 different paths. I net equals I1 plus I2 plus I3 plus I4. Okay, so what? Well, V equals IR. If you solve for I, I equals V over R. Now you see where that R is in the bottom. So I net equals V over R net equals V over R1 plus V over R2 plus V over R3 plus V over R4. In parallel, voltage is constant, so all those voltages cancel out. That doesn't mean it's a 0. It means it's a 1 up top. There you go. So that's the derivation, y'all, for those that are curious. Voltage, it is a good opportunity for me to remind you all, voltage is constant. The voltage across this is the same as the voltage across this, same as the voltage across this, same as the voltage across this, same as the voltage across the net resistor. They all get the same voltage, so those V's just go away and leave behind a 1. You don't need to know the derivation. Anytime I derive something for y'all, you don't need to know that. But as a physicist, it's kind of important to remind you all that everything we do in this class comes from logic. There's logical steps that lead us through every single process and get to every single equation we have. That's the whole idea behind physics, is we explain the entire universe from foundational observations and work our way from there. All right, so can I remind you all of all the main points, and then we'll do a couple problem solving, maybe 1, maybe 2, we'll see the time. So junction rule, current in equals current out, current is conserved. Loop rule basically just says that as you go through a whole loop, the voltage drops all add up to give you what voltage you started with. Resistors in series, current is constant, and you add up the resistors, get the net resistors. Resistors in parallel, voltage is constant, and we have that 1 over R net equals 1 over R1 plus 1 over R2 plus 1 over 3, yada, yada, yada. So all the things we solved so far, this is the main things, and we'll use these to solve a couple problems. The good news is, next class when we get to capacitors, there'll be a couple new concepts, but this is the bulk of the concepts we needed to know. And this is, in my opinion, really kind of useful information to help us understand voltage and current better, which you all interact with every single day, whether you like it or not. And some of this will also potentially relate to when you think of ion transport and things like that in a body, or you think of blood veins, kind of the same idea, except instead of the word voltage, you may use the word pressure. So the word current, it's blood flow. The same logic applies with electricity to blood. Same idea. All right, so first problem solving. Given a 48 volt battery and a 24 ohm and a 96 ohm resistor, 2 different resistors, find the current and power for each when connected in series. Repeat when the resistors are in parallel. Resistances, resistors. So this is a pretty simple kind of setup. We'll draw the pictures, we'll solve through it, but there's nothing too fancy here. I believe the next one we do will be the more complex one. We'll see. We'll probably get to that next class. We'll probably start next class with that, and that'll be a good reminder of our concepts. Here we have series and parallel together. I just want to show you all that it's possible. Next class we'll do that one. So let's start with one that's nice and simple, and let's just practice some of the ideas that we've talked about today, though. This is DC circuits number 2. So we are in problem set number 2. Everything you all should be doing at this point, problem set number 2, up to the next test. So given a 48 volt battery, let's draw a picture, because that's always our first step. There's our battery, and a 24 ohm and 96 ohm. We have to do it for a series and do it for a parallel. So here's my series. These little squiggly lines are resistors. They are not pretty, but you get the idea, hopefully. So that's 48 volts, that is 24 ohms, and that is 96 ohms. And I keep fudging that. All right, so let's just do the series for now, and then we'll repeat the whole thing. I'll draw a picture. So that's our step 0. Step 1, right, our givens. So we know our net voltage. We could call it the battery voltage, but I'll use the term net, because the battery voltage will pretty much always be your net voltage, 48 volts. R1 is 24 ohms. R2 is 96 ohms. So that's everything given in the problem. Step 2, we are solving for 2 things, the current and the power for each. Now, I have an I1 and an I2. I want you all to quickly remind yourself which one, see if you remember which one is constant in series. Is it voltage or is it current? So good. This is really important for you to remember which one is which. You will technically, of course, be able to put it on your note card on the test and quiz and stuff like that. But this is one that, if you haven't memorized, your life will be so much easier when you're solving these problems. So if you thought to yourself current, you were correct. They have the same current. We don't know what it is. I1 equals I2. And in fact, I'll even put I net. I net is the current through the net resistor. I net equals I1 equals I2 equals question mark. They're all the same though. The power will not be. The power will not be. So we need to find the power through resistor 1 and the power through resistor 2. All right. See if you all can think of what equations you're going to use for this. Rack your brain. See if you can figure out step 3. What equations will let us get current? What equations will let us get power? Power is a throwback. We haven't seen that in the lecture today, but we used that last time. That was the last step we talked about. All right. If you recognize we're going to use V equals IR, awesome. Just prepared. Pretty much every one of these problems, you're going to use V equals IR. That's going to come up. Now, the power one, you have choices. You have P equals IV, you have P equals I squared R, and you have P equals V squared over R. How do we know which one to use? Let's start solving the problem, and we'll figure out which one is the easiest for us to use as we go through it. That'll help us determine. But there was 3 different ways to write it. We'll figure out when we're solving which one is the easiest for us to use. Let me drag this over to the side so I give myself some more room. So right off the bat, how do we get current? When you all have a circuit like this with multiple resistors, your first thought should be, I need to combine these resistors. Your first thought should be, I need to combine these resistors. That's pretty much how you can do every single one of these problems. You need to combine them and simplify your problem. So I need to take that circuit and condense it into one circuit. Condense it into, and you know what, actually I'm going to move this thing on back because I'm going to do that over here. You need to condense it into one resistor. Why? Because that's the only way you're going to be able to get the current. I showed you all that previously. If you don't remember, that's okay. You're going to see it again. Here's my 48 volts. Here's my R net. And basically, why do we do this? Because the voltage of the battery will be the voltage of this resistor. I can then use V equals IR. Ta-da! Get the current. The current will then work backward. We'll get to that. I won't go too quickly. All right, let me copy all this and go to a new slide so I have space. But that is the name of the game when we're talking about circuits with more than one resistor, is you need to simplify it to one resistor and work your way backwards. That's how we're going to do every single one of these crazy circuit problems. All right, so step 4, let us get that net resistance. So V net equals I net times, first step. There is one more equation we need to use. It's kind of hidden. At no point did it ask for net resistance, but as I just said, you're going to need to find it. Just get in that mindset that when you're solving these circuits, you need to condense it. So let's get that R net first. R net equals R1 plus R2, very straightforward, 96 plus 24, and that's even super nice numbers, 120 ohms. Series, simple, done. Add them on up. Why did we do that? V net equals I net times R net. I'm just putting all the same subscript next to it. V1 will equal I1 times R1. V2 equals I1 times I2 times R2, so on and so forth. Let's rearrange this to solve for current because we know V. So I can get the current by taking that voltage and dividing it by that resistance. So 48 over 120. That is not a nice number. It's not a terrible number. What is a nice number? Well, actually ended up nicer than I thought. 0.4 amps. Great. And so what was the point of this? Well, we remember in our series circuit, if we go backwards, our current is the same everywhere. So if you have the current through the net resistor, you have the current everywhere. You have the current in R1, R2, the battery, every single point in the circuit that you could possibly ever care about. I net equals I1 equals I2. In a series circuit, current is the same. That's why I was really pushing that concept. You need to know that to be able to solve these problems. Current is the same. Bam! There's the current. And now we can reflect and think, which power equation should I use to solve for the power loss and power? And the first one and the second one, look at what you got. Do you know, actually, you all think about this, do you know the current, the voltage, or the resistor values? You know 2 out of those 3 of those. I'll give you a hint. Let you all think, which one is the easiest one for you to use? Technically, you can solve for the third missing one and then use that equation, but which 2 do you have? Do you have the current and the voltage across each resistor? Do you have the current and the resistance of each resistor? Or do you have the voltage and the resistance of each resistor? Whichever one you have both of, use that one. Save yourself some time and effort. If you chose the second one, you chose the good one. You know the current, you know the resistance. So if I want to get P1, P1 is going to be, again, you just use the same subscripts. I1 squared. P1 equals I1 squared times R1. So 0.4 squared times, what is R1? 24. Equals the number. If I want to get P2, I do I2 squared times R2. Equals 0.4 squared times 96. Just plug and chug. First one should come out to 3.84. We got to remember our units. That's watts. And the second one will be 15.36 watts. The one with the higher resistance, if it's in series, it's going to heat up more. All right, y'all. That was a good amount of concepts today. But kind of look over these. Look at that main point slides. Series, parallel, what the difference is between them, how current changes, how voltage changes. Next class, we'll do some more complex problem solving and then talk about capacitors in series and parallel. I know it looks like we have a bunch of slides, but really we don't. It's just kind of repeating it for capacitors and then solving some problems. We'll talk about RC circuits very briefly, but really won't spend that much time. So basically we'll just do a good amount of problem solving and talk about capacitors next time in series and parallel. If you have any questions, feel free to come on up. As always. Yeah, it's exercise.